Hello there, I'm Derek Hitchins and I'm going to look at what is a systems methodology, or if you prefer, a systems engineering methodology. As usual, I shall be asking my good friend that I like to call Socrates to investigate with the experts what they think about it. Socrates, yeah, are you there? Hello there, me again, your roving investigator. This time I have been asking the experts about the concept of a systems methodology, a single, universal approach to creating systems, or what you might call the how of systems engineering. Here are some of the responses I got. It is inconceivable that there could be just one way to create systems. There are so many different kinds of systems that it makes no sense. Yes, that's it, it's nonsense. Someone is always trying to tell us how to do systems engineering, but there is no particular way. We just make it up as we go along. Really? So what is systems engineering then? Well, it's whatever we say it is, or needs to be, to satisfy some customers' requirements. Customers are all different, so there can't be any such thing as a standard systems engineering methodology. Are you saying that you just make up systems engineering as you go along to meet the particular situation? More or less, yes. So what does it mean to be a systems engineer then? Doesn't that involve particular skills or a discipline perhaps? No, systems engineering is whatever we do in industry. And that makes it part project management, part engineering management, part engineering, and even part muddling through sometimes. I see. So what about these various standards, methods and tools for systems engineering? Don't they suggest that there is some methodology, or at least a particular method? Perhaps, but we certainly don't have a set method. We just get on with the job of meeting the customer's requirements, using off-the-shelf equipment wherever we can to save time and money. No, that doesn't sound much like top-down systems engineering. What about optimizing the solution design? What about measures of effectiveness? Look, systems engineering is just engineering done properly. So there is no systems methodology, there's just engineering. What if I were to suggest that systems engineering is nothing specifically to do with classic engineering, that systems engineering can address organizations, people systems, and so on? Well, we wouldn't want to be rude, but you would be talking through your hat. Sometimes I wonder why I bother. Thank you, Socrates. What about that then? Before we look at systems methodology, we ought to find out what is systems engineering. No, not what people say it is. What is it really? First, it is definitely not program management, nor project management, nor systems management, nor engineering management, nor is it confined to engineering either. Essentially, systems engineering transliterates as wholes creating, or synthesizing wholes or systems from interacting parts to perform with optimum effectiveness in their operational environment, if you want the full version. Essentially, you go from a conceptual whole, using the systems engineering idea, method, approach, whatever you like to call it, from a conceptual whole to an operational whole that performs optimally in its operational environment. So it's from a conceptual whole to a real tangible whole system. And the conceptual whole emerges from an issue, a problem or a situation. What do I mean by emerges? We'll see. Imagine we're exploring the problem space, and the problem space can be looked upon as an n-dimensional landscape. A problem is represented by a break or a pitfall in the smooth, ordered surface. The problem has a complementary solution. It is, as it were, what you would need to fill in the gap in the n-dimensional landscape. This is in the same sense that a key is complementary to a lock. A key isn't a lock, a key undoes a lock, but there's a complementary characteristic about them in that the shape of the lock complements the shape of the key and vice versa. So the nature of the problem leads to the form and function of a conceptual solution. But does the conceptual solution need to comprise the same stuff as the nature of the problem? Well, not really, any more than a key needs to be made of the same stuff as a lock, or what you fill in a pothole in a road with needs to be the same substance precisely as the road was made from. It's not like that. So systems engineering conceives a whole solution to a whole problem, chooses the parts from which to synthesize that whole solution, orchestrates the interactions of the parts, and creates a unified, unitary whole, which operates throughout at the level of the whole, but it's not particularly interested in the internal parts of subsystems, for example. So the systems methodology has to enable all of these things: conceiving, choosing, orchestrating, creating, and operating. Let's look at it from a diagrammatic point of view. In the diagram you can see a problem space at bottom left and a solution space at bottom right. And really what the systems methodology does is conduct the systems engineering enterprise from the problem space to the solution space. So we go through issues and symptoms, conceptual remedies, finding the purpose of the solution system, threats to that purpose. We'll miss out generic reference model for a moment. Then we go to functional design, functional to physical mapping, and the design manifested, that's created, organized, trained, whatever it is. And then we get into the solution space. And the systems methodology is actually the how of going from the problem space through all those steps to the solution space. So there are in the systems methodology skills, techniques, tools, paradigms, processes, methods, organization. In order to make this particular, to work in a particular case, of course, the people concerned within the systems methodology have to have domain knowledge, and they have to have context. Knowledge of context is important too. I was going to mention the generic reference model. That's a sort of model of any system which you use as a model, as an instantiation or something to be instantiated as you go through. I'll explain how that works as we go. There's a generic issue, and from that we can produce a generic conceptual whole solution, and then we produce the systems methodology to work on this generic problem, and from it we can produce a generic reference model of the solution system. Because this is all generic, because we haven't done anything to anything particular, what we've worked out is a method which is scale independent, type independent, and context independent, so works for any system. Of course, for a real system, you have to have domain knowledge and contextual knowledge. And it's those that turn this generic system into a real system. This generic reference model we'll look at briefly. You can see from the reference where you can see a lot more of it. That's on my website. Now, any system can be thought of as being, doing, and thinking. All systems have some sort of being. Some systems not only have being, they are capable of doing things. And some systems have not only got being and capable of doing, but they also are capable of thinking. You happen to be sitting inside a system that has being, doing, and thinking. And lots of systems are like that. You could say that a modern airliner flying around in the sky certainly has being, It's doing things, you can see that. But because of the crew in there, it also has the ability to think. And so it will respond to stimulus. For example, if it observes a major thundercloud ahead, it will deviate, go round it, and go on to its destination without going through the dangerous area. It's thinking. And most socio-technical systems have the three elements: being, doing, and thinking. They're not separate, of course, they're simultaneous aspects of the whole. Now, in order to create a system, we have to look at some paradigms. On the left we have the general problem-solving paradigm, which, as you can see, goes from issue at the top to what they call potential improvements at the bottom. And the idea is that you use the problem components to create an ideal world. You compare the ideal world with the real world that you have and use the difference between the two as an agenda for change. In other words, you try to move from the world that you've got with all its problems towards the ideal world, which doesn't have any. You actually create the ideal world from the problem themes. That's the trick. That's very popular in the USA and it's very powerful, if rather abstract. Notice that it also concentrates very much on the problem and very little on the solution. On the right hand side, on the other hand, we have the systems engineering problem solving paradigm, which is the other way around. It has very little to say about the problem, solving the problem, but it does have lots to say about creating the ideal solution. So we define a problem space and we identify ideal solution criteria and conceive solution options, trade-off, select some preferred option. That's optimization. And we formulate strategies and plans to implement the whole thing. That's the systems engineering problem-solving paradigm. If we put the two together, we get the paradigm that I've used for the systems methodology. It starts at the top with an issue, and it ends at the bottom with an issue or problem solution. And as you read through that from top to bottom, you can see how it's put the other two together into a coherent whole. That will form the basis of what follows. We're going into the systems methodology, level 1. It's a behaviour diagram, and you'll recognise, no doubt, that the central panel is a series of steps or processes or procedures, and each of the steps requires some input at the left to give it something to work on, and it produces a product at the right. So at the top we have number 1, explore the problem space and identify a remedial solution, and the input to that is the rigorous soft methodology, of which more anon. Issue symptoms, factors that make this particular situation special, domain knowledge, and context, of course. And the output would be an n-squared rich picture, a systems interaction diagram, and what we might simply call a remedy, which would be the conceptual whole. Then the step 2, explore the solution space. Step 3, focus purpose. Step 4, develop the ConOps. Step 5, design the putative solution system in terms of functional architecture, physical architectures, and so forth. Step 6, optimize the solution system design. And 7, create and prove the solution system. So we've gone from 1 to 7, and we've covered the whole scale of in to out. You can also see, if you think about it, the systems methodology paradigm in there. Now I could go through each of the steps in turn, but there's a lot of detail in here and it would only bore you. You need to read them at your leisure. That's step 1. Identify, bound and explore the problem space and derive the remedial systems concept. And you can see that the input is symptoms of the issue, problem and dysfunction, and the output at the bottom is a remedial system solution. Step 2 is explore the solution space constraints, which is very straightforward. Step 3 involves the triad building system, which is mentioned as an input at the level 0. And the ConOps, concept of operations, also quite straightforward once you see it in this form. Before we go on to the next step, I just want to look at how you organize these various functions and so forth. Around the outside of this setup we have primary mission functions. These are the functions that an external observer would observe the system doing. So for example, if it's a human being we were talking about, primary mission function would be standing, walking, talking, running, whatever. In order for those to work there would need to be sensor coordination, motor coordination and execution coordination, presuming that we were doing something like going from a sitting position, crossing the street and going to the pub on the other side of the road. That would require execution coordination. And then we can see that the function management, we've got mission management, viability management, making sure the whole system remains viable, and resource management, making sure we're fed and watered, and behaviour management. While this works for a human, it actually works for pretty well any complex system. Now, step 5, functional and physical system design. First thing you can see on the functional design there is that we're organising the various parts and instantiating them along the lines of the layered model you've just seen. And the output of this is a functional architecture, functional interfaces, and the solution system in context. We map the functional system onto a physical partitioning system, so we get a functional physical design set. So that's the functional and physical architectures. Now, before going on to the last step, I wanted to do design by cumulative selection. Here we consider two systems. They're identical in the beginning, red and blue. Red is held constant throughout this dynamic interaction. Blue is initially constant, but is constituted by a number of genes. So if we were talking about a military system, for example, one gene might code for radar, another gene might code for a number of men in an infantry platoon, and so on. All the different parameters that go to make it up. So that in the end, when all the genes are at their nominal values, you have blue force, which is identical with red force. The two forces are made to interact, or compete, or whatever, in some way, a number of times in some model, combat model, competition model, or whatever. And over a large number of runs, they should end up getting equal performance, since they're identical models, and they're operating in an identical environment. Okay, then we start the design by cumulative selection process. We use a random pattern generator to set the genes to different values. Red, however, is kept constant. The result, as you can see from the bulleted there, some combinations of genes produce less effective blue, some more effective blue. So we select those genes that lead to a better blue, repeat the runs, watch blue's effectiveness gradually grow and grow as we repeat the process. Eventually we end up with a set of genes that is the maximum effectiveness of blue compared with red. Red, remember, was its original self. So we have effectively now optimized the design. We could go further, of course. Having got the optimum design in blue, we could now put in a different force instead of red, or a different competition instead of red. Something quite different, and see how we got on. And we could once again try and evolve blue force to do the best it could against that new red force. So we can actually try out different ways, develop different strategies, and develop different capabilities. It's a very powerful system. So there you see optimizing the solution system design by cumulative selection, presented this time
as a straightforward behaviour diagram. And the final step, step 7, create, prove and set to work. That's exactly what you think it is. We bring the whole parts together. We test, integrate, work out the systems. We prove the full solution system. Manufacture, field, commission, deploy. Support through the mission or through life, if necessary. Reconfigure, redesign, upgrade, adapt, repurpose. And eventually we will retire, scrap, recycle and replace. And that's the whole thing from beginning to end. If we now look through top to bottom, we can put all the strategies that we've employed here within the systems methodology together. Find the root problem, conceive remedial solutions, define the solution space, establish the prime mission functions, define internal functions, functional architectures, map functional onto physical, optimize the whole design, specify the whole contained parts interactions as one, acquire, create, train and organize, prove, deploy, support, enhance, evolve, and of course eventually decommission. So there's the whole thing in one from a strategic point of view. So there's the systems methodology. Does it incorporate the people? Does a methodology include the people? Does it include their organisation and the management of product, process and practice, methods and tools? Should it? Is it actually multidisciplinary, as people insist? Or is the discipline in here systems engineering? Is the knowledge that's involved here general, or is it systems science? Should it be systems science? If not, why not? Does all of this match what you've been experienced and what you've been taught? I have a sneaking suspicion. It's complete and comprehensive. However, to employ it needs a full understanding of the domain and the context. And I mean full. Knowledge of how to apply the tools and methods. Creative minds, drive, energy and organisation. And practice. How do you get to Carnegie Hall? Lady, you've got to practice. Given the above, you can tackle any issue, problem, situation, and with luck, some help and a following wind, you should create the solution. Here you can see the systems methodology at level 2. This is as a series of activity boxes, all numbered so that we've got a way of managing the process as a sequential set of activities, steps, phases, whatever you like to call them. It can be applied to solve just about any complex problem, social, political, organisational, economic, technological, operational, even cultural. It's system science based, it's rigorous, it's provable, and it's falsifiable. It's tool supported, although it will need future tool development, and it will need time to learn and practice their usage. It is highly creative and innovative. It potentially restores systems engineering to its former preeminence. Overall, I commend the systems methodology to you. It really is the future of systems engineering, if it has any future.